The opening hook, the aerodynamic paradox. Visual, black screen. Audio of a low hum, building to a roar. Suddenly, footage of the F-117 Nighthawk flying awkwardly, wobbly, unstable. Narrator, in 1981, the United States made a plane that was effectively invisible to radar. It was the F-117 Nighthawk. But from an aerodynamics perspective, it was a disaster. Visual overlay of the F-117 with lift/drag vectors. Show the sharp, faceted edges creating turbulent airflow. Narrator. It was famously nicknamed the Hopeless Diamond. To deflect radar waves, it relied on flat, faceted surfaces. It had the aerodynamic efficiency of a brick. Couldn't break the sound barrier. Couldn't turn tightly without stalling. It was a stealth platform, not a fighter jet. Visual cut to a blueprint of the F-22 Raptor. Smooth curves, blended wing body, massive engines. Narrator. 10 years later, engineers were given a new set of requirements that physically contradicted each other. The Air Force demanded a plane that was even stealthier than the F-117, but they also wanted it to cruise at Mach 1.5 without afterburners, pull 9 GS in a turn, and maneuver at angles of attack where normal planes fall out of the sky. Visual, split screen. Left side, stealth, requires angles. Right side, speed, requires curves. The two sides crash into each other. Narrator. This is the story of the F-22 Raptor. It is not just a plane. It is a compromise between two warring branches of physics, electromagnetism and fluid dynamics. Visual, image of the F-22 Raptor planform view. Narrator. Today we aren't looking at the missiles or the guns. We are looking at the skin, the shape, and the flow. We are going to calculate why this machine, arguably the most expensive fighter ever built per unit of weight, shouldn't be able to fly the way it does. Chapter 1. The Radar Cross-Section, RCS, Constraint. Visual, 3D animation of a radar wave hitting a curved surface, like an F-15, and scattering everywhere, then hitting a flat plate. Narrator. To understand the aerodynamics of the Raptor, you first have to understand the constraint that ruined the life of every aerodynamicist on the project. Radar cross-section, or RCS. Radar works like a flashlight in a dark room. If you shine a beam at a mirror ball, a standard fighter jet with missiles hanging off it, the light reflects directly back to you. To hide, you need to be a mirror angled away from the source. Visual, top-down view of the F-22. Highlight the leading edges of the wings and the tail fins. Narrator. This leads to a design principle called planform alignment. Look closely at the Raptor's wings. The sweep angle of the main wing's leading edge is exactly 42 degrees. Now look at the horizontal stabilizers at the back. Their edges are also swept at 42 degrees. Even the engine intake cowls. Visual. Lines drawn across the aircraft showing parallel angles. Narrator. Every single edge on this aircraft is aligned to a specific set of angles. Why? Because when a radar wave hits the plane, the engineers want to control exactly where that reflection goes, specifically, anywhere but back to the receiver. They bunch the radar spikes into very narrow sectors. Visual, CFD simulation showing airflow over a 42-degree swept wing versus a variable sweep wing. Narrator. But here is the aerodynamic penalty. A 42-degree sweep is great for deflecting radar X-band waves. It is not the ideal angle for maximum lift at low speeds, nor is it the ideal angle for minimizing drag at Mach 2. By locking the geometry to satisfy the radar equation, the engineers lost their ability to optimize the wing for pure flight. They were starting with a handicapped wing design. Visual, image of F-22 stealth edge alignment. Narrator. So, how do you make a handicapped wing generate enough lift to turn a 30-ton metal object on a dime? You have to cheat the air. Chapter 2, Vortex Lift and the Chins. Visual, smoke trail test footage of an F-22 at high alpha, angle of attack. Swirling vortices forming over the wings. Narrator. If you look at the nose of the F-22, it doesn't have a circular cross-section like a commercial airliner. It has a sharp, distinct ridge running along the side of the nose, blending into the wing root. These are called chins. Visual. Diagram showing the chine, generating a vortex that energizes the boundary layer over the main wing. Narrator. In normal flight, air flows smoothly over a wing. But when a pilot pulls back on the stick to make a sharp turn, the angle of attack increases. Eventually, the air can't follow the curve of the wing. It separates. This is a stall. You lose lift and you fall. The F-22 lives in the post-stall regime. Visual. Close-up of the State Route 71 Blackbird nose. Then transitioning to the F-22 nose. Narrator. Borrowed from the State Route 71 Blackbird. The chins on the Raptor act as vortex generators. As the plane pitches up, these sharp edges slice the air, creating massive, spinning tornadoes of air vortices that travel over the top of the main wings. Visual. Fluid dynamics simulation. Low pressure, blue. Inside the vortex core sucking the wing upward. Narrator. These vortices are low pressure zones. Because pressure is lower on top of the wing than below it, this creates massive amounts of lift even when the wing should be stalled. This is vortex lift. It allows the Raptor to maintain control at angles of attack exceeding 60 degrees. Most planes lose control at 20. Visual. Image of vortex lift simulation. Narrator, however, there is a trade-off. Generating vortices creates induced drag. It is energy-intensive. It bleeds speed. In a dogfight, bleeding speed is usually a death sentence, unless you have an engine that can brute force its way through the drag. Chapter 3, Supercruise and the Area Rule. Visual. Graph comparing F-15 thrust versus F-22 thrust. Then a fuel consumption graph. Narrator. This brings us to the Pratt & Whitney F-119 engines. These aren't just engines. They are industrial miracles. But the engine alone isn't enough to achieve supercruise, the ability to fly at Mach 1.5 without using afterburners. Visual. Animation of the transonic drag rise. A wall of air building up in front of the plane at Mach 0.9. Narrator. To break the sound barrier, you have to overcome wave drag. As you approach the speed of sound, air compresses. It forms shock waves. These shock waves suck energy out of the aircraft. To minimize this, engineers use the Whitcomb area rule. Visual. A diagram of a Coke bottle. Then an overlay of the F-22 fuselage, showing the wasted shape near the wings. Narrator. The area rule states that to minimize drag at transonic speeds, the cross-sectional area of the aircraft must change smoothly. Where the wings stick out, adding area, the fuselage must pinch in, removing area. Visual. Top-down view of the F-22 again. Highlight the weapons bays. Narrator. But the F-22 has a problem. It can't carry weapons on the wings because that ruins the stealth shape. It has to carry them internally. This means the fuselage has to be fat enough to hold missiles and fuel. Visual. Wireframe showing the internal packing of the F-22. It is incredibly dense. Narrator. The engineers had to mathematically sculpt the fuselage to adhere to the area rule while stuffing two massive engines, side weapon bays, and a main weapon bay into the airframe. The result is a fuselage that looks flat and wide, blending seamlessly into the wings to spread out the shock waves. Visual. Image of shock waves on aircraft. Narrator. This shape allows the F-22 to slice through the air at Mach 1.8. Why does this matter? Kinetic energy. A missile launched at Mach 1.5 has significantly more range and no escape zone than a missile launched at Mach 0.9. The aerodynamics of the plane actually make the weapons deadlier. Chapter 4, Thrust Vectoring and the Thermal Nightmare. Visual. Rear view of the F-22. The nozzles moving up and down. Narrator. But the most distinct aerodynamic feature is at the back. The 2D Thrust Vectoring Control (TVC) nozzles. Visual. Diagram showing the difference between aerodynamic control surfaces, elevators, and thrust vectoring. Narrator. At very high altitudes, the air is thin. Control surfaces like elevators and rudders become sluggish because there isn't enough air pushing against them. The F-22 solves this by pointing the explosion. By angling the exhaust nozzles up or down by 20 degrees, The F-22 can pitch the nose up even if the plane is moving at 0 miles per hour relative to the air. Visual: compare F-22 nozzles, rectangular, to Su-35 nozzles, circular/3D. Narrator: Russian jets like the Su-35 use 3D vectoring. They can point anywhere. The F-22 only uses 2D, up and down. Why accept this limitation? Visual: infrared camera view of a jet fighter. The round exhaust nozzle glows white-hot. Narrator: stealth isn't just about radar. It's about heat. A round nozzle is an omnidirectional beacon for heat-seeking missiles. It allows a direct line of sight to the hot turbine blades. Visual: diagram of the F-22's duct, intake, and the rectangular nozzle geometry. Narrator: the F-22's rectangular nozzles do two things. First, they facilitate mixing cool outside air with the hot exhaust gas, flattening the thermal plume and making it harder to track. Second, the shape aligns with the sawtooth trailing edges of the wings to maintain that critical radar stealth we talked about earlier. Visual: image of F-22 thrust vectoring nozzles. Narrator: the engineering cost here is extreme. These nozzles have to withstand temperatures of 3,000 degrees Fahrenheit while sustaining the mechanical stress of vectoring 35,000 pounds of thrust. To do this, they use ceramic matrix composites and active air cooling systems that bleed air from the compressor to cool the nozzle flaps. It is a thermodynamic nightmare to keep these things from melting. The verdict: the cost of perfection. Visual: montage of F-22 maintenance crews scrubbing the surface. Charts showing cost per flight hour, $70,000+. Narrator: the F-22 Raptor is widely considered the greatest air superiority fighter ever built. But from an engineering standpoint, it is a cautionary tale of diminishing returns. Visual graph showing the asymptotic curve of performance versus cost. Narrator: to achieve the aerodynamic perfection required to be both invisible and supersonic, the F-22 sacrifices maneuverability and maintainability. The radar-absorbent skin is fragile. The specialized nozzles are maintenance hogs. The first principles of physics dictate that you cannot have high performance, low observability, and low cost simultaneously. Visual: the F-22 fading out, replaced by the F-35 and next-generation air dominance, NGAD, concepts. Narrator: the F-22 proved it could be done. It proved we could cheat the drag equation and the radar equation at the same time. But it also proved that the limit of aviation isn't always the speed of sound or the strength of materials. Sometimes the limit is simply, how much complexity can a logistical system handle? Visual: final shot of F-22 breaking away from camera, afterburners lighting up. Narrator: the Raptor is an aerodynamic masterpiece, a sculpture of titanium and composite that forces the air to do its bidding. It is the physical embodiment of compromise nothing, and the staggering bill that comes with that philosophy. I'm Name, and this has been a deconstruction of the F-22 Raptor. Visual: end card. Deep dive: the geometry of air inlets and S-ducts. Visual: a tracking shot moving slowly toward the F-22's air intake. The camera pauses right at the lip of the intake. Narrator: if you want to understand why the F-22 costs $150 million, don't look at the cockpit. Look at the air intakes. In a normal fighter jet like the F-15 or F-16, the engineering goal for an intake is simple. Get as much air as possible to the engine face with as little turbulence as possible. The straightest path is a straight line. Visual: diagram showing a straight intake duct. A radar wave enters, hits the spinning turbine blades, and reflects out. A massive radar spike graphic appears. Narrator: